Welcome back to the DIP lectures. Today we are having a lecture after a break. I hope your exams had gone well, and once again, a very good morning to all of you, and a very happy new year too. Now, we have covered quite a lot of grounds in DIP, and just to summarize very quickly, we started with the historical background of digital image processing. We saw what had happened in 20th century, in at least the first half of the 20th century, and we have also seen what are the different spectra which are available for taking images, which are available for different domains from where the images are available for processing. So these are the various different things that we have seen. We have also seen the mechanics of human eyes, and we have also seen how different mechanical system or camera system acquire the images. This was a sort of a background to our course, and then we started with the mathematical construction of our course. We have seen that an image is a set of numbers in two dimensions, each number having x and y position and an intensity value. So once we have defined the image in that form, in that fashion, in that way, we can go ahead and process the image. Now, processing has multiple ways we have seen. One of the ways was the single pixel operation, or simply called as intensity transformation, and we have seen many of them like thresholding or making a binary. Then we have seen the increasing the contrast by piecewise operations, inverse operations, gamma functions, log functions. So these are transformations we have learnt. Further, we, instead of single point or single pixel operation, we moved on to the operations which involve a subset of pixels. And the mechanics used to implement those kind of operations we have seen are correlation and convolution. So we have understood correlation process, we have understood convolution process and their mathematics as well. After that, we did some sort of spatial filtering methods using convolution and correlation. One was smoothing filter, which we had also called as a low pass filter, where the minute details were suppressed while big details were retained. And we have actually learned two kinds of kernel. One was the box kernel, all elements being 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, something like that. If it's 3 by 3, or if it's 5 by 5, then you give one more padding of 1. So we have used box kernel, and we have also seen the Gaussian kernel, which is a radially symmetric kernel. So we have learned these two, softening or blurring filter, as we can call them in day-to-day language. Technically, they are all low-pass filter. When you go towards Laplacian and gradient, you are going towards a high pass filter. They enhance the fine details but suppress the broad picture, the big details. So they are called high pass or high frequency pass filter. So one can use it when you want. And we have seen how to apply an unsharp mask. So I think apart from these, we have seen the use of median filter, max filter, etc. So that's what we have already done so far in this course. Now in today, we are going to have another overlook of frequency domain filter, a slightly different perspective than we have learned earlier. And again, I will remind you that our operations right now are all in spatial domain, although we are calling them the frequency domain filter. As we get into the next chapter, we will see that which is on frequency domain filtering, we will actually see how it turns out. And we are going to see how we can combine different methods to get some sort of final result. Okay, so going ahead. So here are my frequency domain filters. Let me clarify once again the word use of the word frequency here. Now, in an image, any feature which is large compared to the size of the image, well, now uh, it would be nothing can become bigger than the size of the image, obviously. But suppose if the size of the image is, say, 10 inch in some dimension, say along x dimension, and if you have some sort of image element which runs in 2 inch or 3 inch, like that, like a fence or a grill, which turns out to be of 2 inch width in an image, then it is going to be a low frequency component of the image, because large objects in an image would repeat them fewer number of times. Small objects, suppose if there is a tree and there are leaves on the tree, then these are the small objects in the image, and they are going to repeat many times in the image. So a tree can have thousands of leaves all coming in the image. You might click a pattern which may repeat itself, say, 100 times in an image. So the point is, when you say frequency here, we are we have nothing to do with time, for example. I mean, that has to be very clear in your mind. Normally frequency is defined as 1 upon time period, but here we are not talking about time. Here frequency is defined something that if an object is repeating itself more often in an image, then it will, we say that it has a higher frequency. If an object is repeating itself less often in an image, then it has a lesser frequency. So that's how we define frequencies. Nothing to do with time, no 1 upon time period. In the next chapter, when we do, we will look at the exact reason why we still call it frequency. Now, the frequency domain filters typically have these parameters or these characteristics. So we have a low pass filter. In a low pass filter, at a certain cutoff, beyond that all the frequencies are blocked, while before that all the frequencies are allowed. So typically this is a profile. This profile multiplied to the frequency spectrum. So you can see that the value is 1, which is maximum here, up till u0. So 1 multiplied to any frequency component will not alter its value, so it will remain the same. After that, all the values are 0. So 0 multiplied to a frequency component will make all the values to be 0. So you can see that whatever cutoff you choose, your all the image components lower than that cutoff will be allowed to pass through. They will not be altered, while anything above that cutoff will be blocked. Now this is, remember, what I'm showing you is an ideal response. In practice, the response is never so cornered and so sharp. There would be some sort of falling off, which is typically referred as a roll off rate. So that is a possibility there. Then once you have your low pass filter, so what we have learned, a box kernel, that is all one, those kind of kernels, or a Gaussian blur kernel will give you this effect. So these are all spatial operations. They happen in spatial domain, but their impact is to uh, suppress the finer details. They're all blurring filters. So their impact is to suppress the finer details. Sorry. So finer details means higher frequencies are suppressed, while they tend not to change the lower frequencies, that is larger objects in the image. So that is how they work. So they are the examples of this kind of filter. How do you get a high pass filter? So the definition is opposite. So to a definite cutoff frequency, all the components are blocked by multiplying it to 0, and all the components are allowed after that, beyond that frequency. So if this happens, then it's a high pass filter. You can see that you can easily obtain the high pass filter from the low pass filter. Can you think how? So well, you can see that this is up 1 up till here and 0 here, and this is 0 here and 1 here. So if you take a low pass filter and if you subtract it from the 1, 1 is the maximum value. These are all normalized functions. So 1 is the maximum value. It is something sometimes also called as an impulse value or a delta value, something like that. So if you subtract your low pass filter from 1, you will get a high pass filter. So yes, they can, if you have designed your low pass filter, getting a high pass filter is easy. High pass filter, as we have seen, it allows higher frequencies, finer details through the image, suppresses the broad details. Examples of these filters we have learnt are Laplacian and unsharp masking, of course gradient also, I have not written here. So these are the examples of the high pass filter. Okay. Now this is a band pass filter. A band pass filter, I'm sorry, band reject filter. So band reject filter typically has two cutoff frequencies, and one is lower cutoff and one is a higher cutoff. And then anything which is less than U1 will be allowed. So it falls in a band called as pass band. Anything above U1 is allowed. Again, it falls in the band which is called pass band. But anything in the middle of the two cutoff range is not allowed, and it is called stop band. Now, practically, it is not again this sharp. You will find that there is a cutoff here. So, I can combine a low pass filter and a high pass filter which are designed at different cutoffs. The low pass filter designed as at a cutoff of U0, and the high pass filter, which is designed at a cutoff of some other value, will combine together, will give you a band reject filter. How do you get a band pass filter from a band reject filter? Straightforward, you take the maximum value, which is called impulse value, and subtract the band reject filter from that. Here it is 1. So you subtract all these filter values from 1, you will get a band pass filter. As expected, the band pass filter will allow you to pass certain frequencies and stop the other frequencies. So you can design all four of them in a suitable way. Here is the mathematical relation. If LPXY, that is low pass filter, LP is low pass, which is a function of x and y. Bracket xy means it's a function of x and y position on the image. So if LP x and y gives your low pass filter, then your high pass filter HP is the maximum. Remember 1 which was there in the previous. Here, as I said, it is also called as impulse or delta. So you subtract from the maximum, and the low pass filter subtracted from the maximum will give you the high pass. And then comes your band reject. So you take two different, you take an LP and HP at two cutoff frequencies and add them together. And when you simply add them together, you will get a band reject filter, as we have seen. And you can substitute for HP, you can substitute this one, and you will get a band reject. A band pass is a band reject subtracted from the maximum. And we have seen the maximum is delta. So band reject subtracted from the maximum will give you the band pass. So I hope this works. This is self-explanatory. Now here is one image. Let me now again get into drill more into the details of high and low frequency. This is an image. Those who have studied optics seriously, they know that this is an image of a zone plate. Now, or if you have seen it carefully, it looks like Newton's ring. Just that the center is dark in Newton's ring. Now, computationally, you can obtain this image by making this computation. So you can take different values of x and y's, calculate their cos, calculate z, plot z versus against x and y in this, and you can put restriction that how much maximum x you want and how much maximum y you want, and you will get circles created. So you can put the values in the Python and plot the graph very easily. So this is the frequency domain. This image is typically used to study frequency domain filters. Now why is it? If you observe it carefully, you will find that towards the center the objects are broad. There is a broad white patch, and the broad black, and then broad red. Broad white another, then black. And as you go towards the periphery, you will find that there is a drop in the thickness. So these broad objects, they hardly repeat. You can see that this broad circular white patch does not repeat anywhere. This width is not repeated. This width again is not repeated. This is there, but you can see that if you are at this end, almost they are all well repeated. So as you go towards the periphery, we will say that the frequency component of the image is increasing. As you go towards the center, we say that the frequency component of the image is in, I'm sorry, I said opposite. As you go towards the periphery, the objects are getting smaller, they're repeating themselves quickly. So we say that the frequency is increasing. As you go towards the center, the objects are getting larger, they don't repeat them so often. So we will say that the frequency component is decreasing. So spatial frequency increases as a function of distance from the center. Now this can be applied different filters and observe effect can be observed. So first I'm going to show you some simple images, and toward the end of the lecture in few minutes I will demonstrate you by running it on a software, and then we will see how it changes dynamically in real time. So yeah, now frequency domain filter, this is one of the examples. So as I said, the last one was the, I mean the earlier image that I showed you here, that here it was a very sharp cutoff. So this line is almost vertical. Practical filters will not be that sharp. So here is one example. This is a low pass filter which is centered in the middle, or origin is at the middle. Remember that. So you can see that it has a high to low value. So the values, this is going to be your pass band, and then this is ideally stop band, but you will find that some ripples are there in the stop band, and you will find because of those ripples not all the frequencies will be suppressed sharply. This is in one dimension, while if I rotate this about this axis, then this gets into two dimensions. So these are my low pass filters which are centered about the origin, which is at the center of the image here or here. Now if I combine my, so two images, like if you take this image and you multiply to this one, not the upper one, lower one, then the result obtained is over here. If you observe it carefully, you will find that all the higher frequencies are grayed out, they blurred out, they got suppressed, while all inside frequencies are retained as they are. So image has been retained. Remember the filter that I showed you is circularly symmetric here. It's an isotropic filter. That is why your impact over here is isotropic. On contrary, this is the result of applying a box kernel. If you remember our box kernel, 1 1 1 1 1 1 1 1 3 by 3 box kernel. So if you apply that, you can see that the result is not symmetric. So if you apply a Gaussian kernel, you will get a symmetric result. You will find that, at these points the lines survive, but here they are suppressed. So that is the difference. But on the whole, you will find that applying these filters will suppress the lines at the boundary, at the periphery, at the higher frequency domain, while in a lower frequency domain, the lines are dominant. These are the different applications. So if you apply a low pass filter, higher frequencies are suppressed. If you apply a high pass filter, you can see then the higher frequencies survive while the lower frequencies are suppressed. So broader details will vanish if you check carefully. And you can see that it has lines because high pass filter is typically Laplacian, which extracts the edges. This is a band reject filter. So where the inner lines are staying outer lines are also staying, but the lines in the middle are suppressed. So this is a combination of a low pass and a high pass at different cutoffs. And then this is a band pass filter where the lines towards the center are rejected, lines towards the periphery are rejected, lines in the middle are put forward or carried forward. So these are the impact of different filters. Now I'm going to show you one example where we can combine the spatial enhancement method. We have got an image over here which is the whole body scan. Now the problem with this image is that it has a very narrow dynamic range. Now narrow dynamic range means the separation between the dark regions and the bright regions. So if that or contrast in a loose sense. So if that separation is less, we say that the dynamic range is less. And if that separation is more, we say that the dynamic separation is more. Also, this image is found to be high, high on noise. So if you zoom in, you will realize that the noise element is fairly strong here. Now, we have to remove the noise. Noise is a high frequency component, but we also need to do sharpening here so that the bone structure can be seen as sharp as possible. So it's a challenging task to us. We can apply sharpening filter, which is Laplacian, but it enhances the fine details. So you sometimes also, dilemma that applying Laplacian will give you the edges, but it also give you the noise. And you can apply gradient. Remember, Laplacian gives you edges, very sharp and fine edges. And for more smoothened out edges, you can apply gradient, especially Sobel. So here is the impact of Laplacian. If you apply the Laplacian, you will see something like this. Practically, you will see a more dark background. I have tweaked it a little bit so that the edges are visible. You can see the noise is there. Lot of noise is also visible. If you enhance one portion, then you can see that the bone structure is edges, but these are all noise, which we don't want. So how do we handle this? So after applying Laplacian, typically one of the steps is to apply a suitable, what you call, smoothing out Gaussian blur kernel. So once you apply that, you smoothened out, you retain the edges depending on what cutoff you are using. Remember, it's a cutoff frequency which is very important. So at one frequency, you get the edges of the bone structure. You can see that the bone structure has a lower frequency than the noise. Noise repeats much faster than the bone. So there has to be a cutoff frequency between the two by which you can separate the two. So typically that separation is done and you add this image to the original one, which you can get this one, which is slightly better. I will show you all 4 or 5 images in one slide and then you will make the difference. And then I can apply gradient operation so that the edges, Sobel gradient, remember the Sobel gradient gives us the smoothing required, because as I said, you will need some smoothing because your noise is enhanced by Laplacian. So Sobel gradient gives you some smoothing, plus it enhances the gradient operation. You can see that this is original, this is Laplacian, this is Laplacian added to the original, and then this is smoothing and gradient. And you will find that the last image gives or brings out the bone structure more prominently than the starting image. Remember, it is all subjective, where to stop. That is one critical question that an image analyst is always subjected to. That with tools available, techniques available, computers available, computing power available, it is very difficult to judge and decide where to stop the image processing. And it is always subjective. So the more you do, more you study others' image, more you work on your own images, more you realize that how it works and how it doesn't and where to stop. It comes with experience. Okay, so we can stop here. Now, don't go back. I'm going to show you, as I said, these operations in a live manner. So I have this image over here, which I can show you these operations. As I said, this is a ready-made software, not for you people. It's a tool for taking lectures because in a real classroom lecture time, it is quick to use, so it saves time. But you have to implement these things in Python. Sorry. So we can go to this. This actually offers me lots of filters. So I can take a box blur, for example. Box blur is, as I said, 111, 111, 111, that kind of filters. Now I can, there is a slider is given by which I can increase the size of the filter. 3 by 3, 5 by 5, 7 by 7. I'll prefer some round figure, although this gives me some decimals also. Now you can see that I'm increasing the size of the box blur, and as you will find that, observe carefully, you will find that the periphery is getting blurred. Look at this. Now this is roughly say 9 pixel by 9 pixel. I will put here. Yeah. This is 9 by 9 box kernel. You will find that this is a low pass filter, smoothing. So you will find that your center is retained while your periphery becomes blurred. Now remember, you have a cutoff here. You can say that the cutoff is somewhere here. That cutoff can be altered. So suppose if I apply 3 by 3, you will find that the cutoff is not there, it is gone out, or it's a very negligible impact. If you look at 5 by 5, some cutoff will come. But suppose you apply 11, then you will find that the cutoff is very quick. All these are blocked here, and these are surviving. Now I will go to 13 by 13, and you can see that this impact becomes more. Your cutoff is now almost somewhere here. All these have become blurred. You can see that this is a box blur, which is not a radial blur. So you will find that this box shaped thing is not circular. And I leave it to you people to think why these have become prominent. So I'm just leaving this for you people to think. Now I cancel this and I go to a filter which is radially symmetric. A Gaussian blur is that filter for me, which is radially symmetric. Again, I can go for a 3 by 3 or 5 by 5, and you will find the impact. You can see that at 5 by 5, the peripherals lines are blurred out, while the central lines are still there that way. So this is how it works. I can again go to say 9 by 9, and only in the middle it is sharp. Here it is blurred out. If you want to go more further, then maybe 13 and see what happens. You can see these are very large objects, so they will not get disappear very quickly. But you can see that at 15 by 15, all the peripheral objects have vanished completely. So this is my cutoff here. I can still see central spot, I can see this bright band, I can see this, but nothing beyond that at 15 by 15. Let me go at 19 by 19. And again the center one is retained because center one is really large. It has a very low frequency. Your cutoff needs to be really very low to eliminate the center one. I'm making it 25 by 25. Center one is still retained. So I'm lowering my frequency of cutoff frequency further and further. Suppose I lower it to 35 and see what happens. Now you can see the center one is almost gone at this frequency. So you can see how changing the frequency will, I'm decreasing the frequency, sorry, I'm increasing the cutoff frequency. You can see that the center appears first, then you can see the bands which come in the periphery are now appearing, and finally all the bands have appeared. So up till like this there is no impact up to 3 pixel. After 3 it starts. So these are all the impacts of low pass filter on this image. I'm doing it slowly so that you all can notice it. Okay, now I'm going to demonstrate very quickly the high pass filter. So as the name suggests, this is the high pass filter. Right now my cutoff is such that nothing is being passed. Now I change my cutoff. You can see that higher frequencies is here my cutoff is 0, so no frequencies are passed. Now I can start changing my frequency. Now high frequency elements are coming. I'm lowering it, and you can see that at the periphery it is sharper and clearer. The center is still blurred. Low frequency objects are not going through. High frequency objects have gone through. So as you go further, you can see that the peripheral elements become more dominant, they become more better in your final image. And then as you lower the cutoff frequency of the high pass filter, similarly slowly even the center element comes through. So I will do it slowly and you can check. This is increasing the cutoff so that in a high pass nothing passes through. Then you start decreasing the cutoff and slowly you allow bands to pass through, and finally the center also comes. So this is the impact of uh, high pass. You can see that I have shown you a high pass and a low pass. You can combine the two effects very quickly. We have few minutes of time to check if it is possible. So I'll go to the Gaussian blur once again, and I will try to take a cutoff here where my peripherals are getting slightly blurred. So I'll keep it at 5 cross 5. I will, oh sorry, I'll go back, take the Gaussian blur, and I will take a 5 cross 5 and apply. So the lines have gone. Now it is applying. Yeah. And then I can go to sharpening. I can go to high pass. And then I will slide it so that my center is blurred. Center spot is blurred, and I will apply. So of course this would need some contrast correction, which I can do very quickly. Yeah, so now you can see at this image, look at it carefully. The peripheral bands are blurred, they are not dominant. The center is also blurred, this is also not dominant. So your very high frequencies are suppressed, very low frequencies are also suppressed. What is retaining is your middle frequency. Your middle frequencies, center frequencies are sustaining. You can tweak, you can adjust the sizes of the low pass and high pass to bring out particularly which band do you want. So that's all from this demonstration. So as I said, we can stop here. Thank you.